Okay, so starting with the dagger that we know from Minkowski space, we've now been able to define a dagger for Euclidean space. And we've called that star. A star of Tor is defined to be equal to the Minkowski dagger, a dagger, evaluated at minus Tor. And a complete summary of our previous discussion, why did we take this definition? Well, it was so that uh, time evolution is unitary. Okay, so meaning um, u star of Tor was equal to u of minus Tor, and that implied that u star of Tor times by u of Tor was equal to the identity. And this was the condition that we needed to preserve the probability interpretation of the theory. So we have taken the definition of the dagger in Minkowski space and we've used it to provide a definition of the dagger in Euclidean space. If you want to have a Hermitian operator, so for a Hermitian operator, so in Minkowski, you would have said that O of t must be equal to O dagger of t, whereas in Euclidean space, you would say O star of Tor must be equal to O of minus Tor. So once again, you can check this just by using the definition that we've given above, but it's good to think through these simple things so that you get some familiarity with our new definition of the dagger. Now, let me just stress one thing. We use our new definition, we use star on the cylinder. And on the cylinder, what is star equal to? Well, if I have to tell you what is star, star means do the dagger, the normal Minkowski dagger, and then Tor goes into minus Tor. So that's what star is. It's that composite operation. So let's just put our dagger here. Here is our dagger on the cylinder. So there's the cylinder, and all of the equations would apply. A star of Tor is equal to a dagger of minus Tor. We would also, let's also talk about how you would take the dagger of, let's say, a state, a ket. So psi of t star. So what would this be? Well, easy. If I ask you what is psi of Tor dagger, you wouldn't even blink. You would immediately turn it into the ket. And then all you need to do is evaluate this ket at minus Tor. So that's how star acts on states. It turns kets into bras and bras into kets and changes Tor into minus Tor. Now, what we want to know is, what do we get if we now map to the cylinder? Sorry, to the plane. So we were on the cylinder. Now let's go to the plane. So there is the plane. If we had equal time slices on the cylinder, these would map into equal radius slices on the plane. And so now on the plane, how do we define dagger? Well, the coordinate transformation that we use to go from the cylinder to the plane says set r equal to e to the Tor. So this is the relation between r and Tor. So in particular, if we look at this rule of sending Tor to minus Tor, what action does it have on r? Well, star acting on r, which is e to the Tor, would change it into e to the minus Tor, which is 1 over r. But we know how we go from 1 over r to r. So r to 1 over r, this is performed by inversion. That discrete transformation, conformal transformation that we've already discussed. So let me just remind you, Ri takes x mu into x tilde mu, which is nothing but x mu over x dot x. And you can easily check that I acting on r takes r into minus r. So on the plane, how do we do star? Well, first we dagger, and then we do inversion. So on the cylinder, first we dagger, and then we change torr to minus torr. On the plane, first we dagger, and then we do I. So, for example, on the plane, if we wanted to calculate a star of torr, what would we do? Well, first we would take the dagger of torr, and then we would apply inversion. For a state, let's talk also about how a state would transform. So if we've got ket psi, first we dagger, that'll change it into bra psi, and then we perform inversion. Now, one thing that I really don't want you to be confused about is that we've applied inversion to the state once, but we've applied it to the operator twice. This is just a property of vector spaces. We discussed this at length last year. Let me just show you one example to jog your memory. So when you think about ket psi of t, this we obtained by applying e to the minus I ht to the ket at time naught. So this was just u of t acting on the initial ket. And this would have been happening in the Schrödinger picture. So this is the kind of formulas that we wrote down when we wrote down Schrödinger picture evolution. On the other hand, in Heisenberg picture evolution, we had e to the minus iht, o of naught, and then we had e to the iht. So this was u of t, o of naught, u dagger of t. And this is what we had in the Heisenberg picture evolution. And this rule that, you apply the transformation to the ket, or you apply u dagger to the operator O, this is just a property about vector spaces, okay? Don't get hung up on this. This is just the difference about how we transform operators in vectors, or equivalently, how we transform matrices in vectors. So you could also get this rule just by thinking about how a normal column vector or a matrix transforms under a rotation in a normal vector space. So this is nothing special. This is what I'm trying to explain is why have we got an I in the star action on an operator, but just an I in the star action on a state. Okay, good. Now let's do one application. I want to look at what is, let's maybe change colors to red. What is P mu star? And this is on the plane still. So P mu star on the plane would be inversion, P mu dagger inversion. Then you know that the momentum operator in Minkowski space is Hermitian. So P mu dagger is just equal to P mu. So now we've got I P mu I. And you have checked in the exercises, and it's a simple thing to check, that I P mu I is nothing but K mu. So on the plane, P mu star is K mu. And you can check it's almost an identical computation that K mu star is just P mu. So the special conformal transformation, when you dagger it on the plane in radial quantization, it goes into P mu. Okay, another thing to say is that I dagger is just I. So this is a real transformation, so no difference between I dagger and I. And also I squared is equal to I. So convince yourself of these two facts. These are two pretty fundamental facts about I, and we use them all the time. So let me show you one place where we would use them. Well, we know that A star is equal to I, A, I. Now let's work out what is A star, star. So what should I do? Actually, sorry, there would be a dagger here. So what should I do? Well, I should take I, then I've got I, A dagger, I. So that's just A star dagger, and then I've got I. Now, to take the dagger of that bracket, I move the order of the factors around. So what the factor that's last, which is an I, becomes first and it gets daggered, but I dagger is I. Then the A gets daggered, that's an A. And then the first factor, the I, that becomes last and it's daggered, but I dagger is just I. Then it's multiplied by I. Well, the I times the I is 1. Then we've got an A, and the I times the I is 1. So we've learned that on the plane, if we dagger, A dagger dagger is equal to A. And I'm sure that you know in Minkowski space, if you take A dagger dagger, that's also equal to A. So this equation that you're familiar with in Minkowski space, it survives for the dagger operation defined on the plane. Okay, we'll continue in a moment.